Yizhe from UC Irvine. He will talk about the characteristic polynomials of sums of random permutations.
Introduction. It's my pleasure to be here. Thanks for the organizer for this wonderful summer school. Today I will talk about joint work with Simon Coast from ENS and Gautier Lambert from University of Norwich about characteristic polynomial of sums of random permutation. So let's first understand what is random permutation. We can take a random permutation uniformly from symmetry group. That's a permutation. And we can write a permutation in terms of a matrix. The matrix will be an n by n matrix, and the ijth entry will be 1 if this permutation map index I to index j. So a simple example, this is a 4x4 matrix. Every row you have exactly 1 non-zero entry. Every column you have exactly 1 non-zero entry. And from this permutation matrix, you can read the information of the permutation itself. In particular, this matrix is non-Hermitian. So what do we know about eigenvalues for this matrix? I take a 50, n equals 50, so 50 by 50 permutation matrix, and you see the eigenvalues are pretty rigid. They are on the circle, and the location is like it's pretty. It's not like a random location, and in fact that's true because we can factor the characteristic polynomial of a permutation, and there's a way to represent this as 1 minus z to the power k to the power of ck, where ck is the number of cycles of length k. So if we look at the location of the eigenvalues, they are all root of unity, but the multiplicity is random. The multiplicity depends on the cycle structure of the permutation. So in fact here, this is the locations are root of unity, but you see some locations are missing, and maybe some other locations have multiple eigenvalues. Okay. And what if we take n goes to infinity? You just see a uniform measure on the circle. And there are more precise results by Wieland and Bahia. You can look at even like the fluctuation of eigenvalues inside any arc. And you can even allow the arc to shrink to 0. And this is also an active area in random matrix theory to study eigenvalue fluctuations. And you can also understand the properties of its characteristic polynomial. Okay. So let's just do one more step. What if we add d independent permutation matrix together? So let's first try d equals 2. And then all the eigenvalues start to spread inside the circle. And there's one trivial eigenvalue outside the disk, because if you take all one vector, you'll get eigenvalue equals 2. Okay. And if we take d goes to infinity together with n, first of a large d, if I remove the trivial outlier, this looks like a uniform measure on this. And so we were in this picture, we're talking about empirical spectral distribution. You just put the delta mass at every eigenvalue. And this is still a conjecture. So for any fixed d greater than or equal to 2, the limiting spectral distribution converge weakly in probability to this so-called Kasten-Mackay law, oriented Kasten-Mackay law. This is the non-Hermitian analog of Kasten-Mackay law for random regular graph when d is greater than or equal to 3. So there's a formula for random regular graph. So interestingly, if you take d goes to infinity for random d-regular graph, this goes to semicircular law. And if you just take d goes to infinity, but when I need to do a proper scaling, I scale everything to be on the compact support, then this will converge to the circular law inside the disk. So in fact, that's true. And it was proved by Basak and Dembo that if I just take some of d random permutations and I take d goes to infinity, the random permutations Okay, so instead of looking at random permutation, they look at independent random hard orthogonal or unitary matrices, and this limiting law was proved for D goes to infinity. And this rho D is the Brown measure of the free sum of the hard unitary. Okay, sorry, I think I confused myself. For fixed D, this is proved. And for growing D, if I take sum of D random permutation matrices, D grows at least polylog matrix. Then the empirical spectral measure converge weakly to the circular law. So let me repeat myself. For fixed D, this limiting measure was identified for hard or orthogonal or hard unitary. But for D growing to infinity, we can say something about random permutation. Okay. So our motivation, because I'm more interested in random graph theory, so my motivation to study this model is to look at random regular directed graphs. It was mentioned yesterday from another talk. So the random directed graph is a random graph such that I fix the degree of the vertices. For directed graph, I need to look at the degree that go out and coming in. So there's in degree and out degree, we fix it to be D for every vertex. There are several models to talk about random directed graph for its fixed degree. So you can do 3 popular models. The first one is called a permutation model. So I can just sum D random permutations, but it might be the case that you will get some self-loop or multiple edges. So conditioning on not having those self-loop or multiple edges, you get a simple directed graph. Another way to generate such model is to look at the uniform model. So if I know all the vertex has fixed degree, it is a finite collection of configurations, then you just draw one graph uniformly at random. And the third one is configuration model. Is a way you can generate some half edges and you create a random matching and you pair all the half edges to get a random graph. So these 3 models are popular model because you can choose whatever you want. And if you prove some property for one of the model, it will hold for other model asymptotically almost surely. So this is some property called contiguity. We can translate statements between the 3 different models. So in particular, if we just look at the permutation models, there's some way we can work with independence. Okay. But if I take D goes to infinity, those 3 models are not related to each other. So the contiguity property would fail. Okay. So for random graph theory, a very important topic is about spectral gap. So we already know if I sum D random permutations, the largest eigenvalue will be D. It's the same thing for random regular digraphs. Largest eigenvalue must be D. But then the more interesting property is this second eigenvalue. So there's an analog of Ramanujan graph to Ramanujan digraph that says if you have a nice bound second eigenvalue, this is a nice property for that graph. And you will get some expansion property. It also controls the convergence rate of random walk on these random digraphs. So what do we know? In 2021, Simon Coase proved the second eigenvalue of random regular digraph is bounded by 1 plus epsilon square root D. And he did it for configuration model, but it works for R model. And the second one is if we take D arbitrary between finite or growing with n, you can prove that the second eigenvalue is bounded by some constant square root. So the order is correct, but the absolute constant is not so explicit. Another big result, a breakthrough in terms of spectral graph theory is the circular law result. So if D goes to infinity arbitrarily slowly, you can show that the adjacency matrix of uniform random regular graphs has the limiting distribution as circular law. This is the this is a sequence of work of Nick Cook and a group of people in random matrix theory. So what's our result? We were not able to prove anything about the limiting measure, but we can show that there's no outlier outside the disk except the trivial eigenvalue, which is D. Okay, so our result says if you take a sum of the independent uniformly distributed random permutations, and D can be between 2 and n to the power little o1. So you can think about a polylog is fine, but we cannot go up to polynomial in n. Then the second eigenvalue is bounded above by square root D with high probability. Okay. So if the oriented Casimir-Mackay law, the conjectural law holds, then this implies there's no outlier except the trivial one. And the Bassa-Cook-Zatumi already proved circular law for some of independent permutations if these growing to infinity. So in their regime, we can guarantee no outlier for the circular law. So this is our result. And let's discuss what are some strategies to prove spectral gaps. So the first strategy is the high trace method. Okay, even for non-Hermitian matrix, you can bound the spectral radius by taking the high power of the trace. So there's a non-Hermitian M, you can take the high power of trace M star to the power K. If I take M, so in Simon's paper, his approach is to create a matrix M that's related to the second eigenvalue of A and control the spectral radius of this matrix M. You need to take the high power K up to the order log n. So it turns out you are trying to control the length of closed walk of length log n. And this works if the degree is fixed because it highly relies on the structure of the random graph. You need some local tree-like property to count such work properly. And this is a similar flavor like the non-backtracking operator approach explained yesterday evening by Professor Collins. Okay, so this is one approach. You can get sharp constant by fixed D. Another approach is this constrainability argument, or in random matrix theory, we know this is called epsilon net argument. So how do you do that? There's one nice observation is that if I calculate the first eigenvalue and first the singular value of A, they are the same. So there's a wild dominance inequality between eigenvalue and singular values. You can bound the second eigenvalue by the second singular value. Now the second singular value is nice. We have a variation formula. You can control the second singular value by doing an optimization problem on the unit sphere. Okay, but I need to take a vector that's orthogonal to the R1 vector because I want to get rid of the effect for the trivial eigenvalue. Then it becomes a concentration problem. I need to fix two vectors and do the concentration of the quadratic form. And that's the hard part because this matrix model has dependence entry. So there's dependent structure, but if you do hard work, you can prove some concentration inequality, then you take union bound over epsilon net. So this approach would work even when D grow with n, but you cannot capture the correct constant because when you pay the union bound, you have to take a epsilon net over exponential many point, that will lose the constant factor. Okay, so today we will introduce a new approach. It was first used in a paper by Boldenov, Shafai, and Garcia-Zelada. They look at the convergence of characteristic polynomial of non-Hermitian random matrices with IID entries. But here we are applying it for this sum of random permutations, which is a matrix model with dependent entries. And that allows us to get a sharp constant. So let me explain what we do with the characteristic polynomial. So instead of looking at just the characteristic polynomial itself, we need to do some scaling. So first of all, I scale A by root D, and I do extra other scaling by root D outside the determinant. And this is the characteristic polynomial, but I wrote it in a reverse order. So the eigenvalues will be if it's an eigenvalue of A over root D, lambda inverse is a 0 of this characteristic polynomial. So it's a reverse characteristic polynomial. This root D normalization doesn't matter for fixed D, but when I take D goes to infinity, it does matter. So the trivial eigenvalue will give you a trivial 0 for this characteristic polynomial. Okay. And for fixed D, there's a target function, a YD, which is a power series with random coefficient. This random coefficient is given by some Poisson random variable. So it looks complicated, but I'll tell you how it comes from later. And the problem becomes the following. So for 50, we can show that this normalized characteristic polynomial converge in log to a random analytic function. The topology is uniform convergence on compact set inside the unit disk. So it's a local compact convergence in terms of random analytic functions. Okay. This analytic function, limiting analytic function, has a random part, which is this exponential minus yd, and yd is given here. And this expectation part, we can compute it explicitly. And the trivial eigenvalue gives you this extra factor, z minus 1 over root. Okay. So why we care about convergence of characteristic polynomial? Because there's a nice Horace theorem tells you if I have a sequence of random analytic function converging on the compact set, then you can talk about the zero set. The zero set as a random measure also converge in law to the zero set of limiting function. Okay, so let's look at back of our limiting function. If you just try to look at the zero set, there's only one trivial zero. So that's very nice. And what can we do? We can just prove the spectral gap in one page. Okay. So first of all, this limiting function has only 1, 0 inside the unit disk, but I need to pick my radius a little bit smaller. Okay, that's the trivial eigenvalue. And then with high probability, I know by this Horace theorem, the characteristic polynomial normalized, the reversed one, has only 1, 0 at 1 over root d. Okay, but we know this is the reverse of the eigenvalue of my matrix A. So A over root d will have no eigenvalue outside the radius of outside the disk of radius 1 over r, except the trivial eigenvalue d. And that gives you the spectral gap. So that's it. And then the key point is to show the convergence, right? If I know the convergence of my characteristic function, automatically I got spectral gap.
But in your statement, you also have D growing, right?
Yeah, we'll prove it in a unified way, but I only stated for fixed D. Now I can prove it later for growing.
Okay.
But it's the same method, same argument.
And the YD becomes something else.
All right.
The limiting holomorphic function, I guess, doesn't have.
Yeah, the Y will be even. Yeah, this moment is a random function with Poisson coefficient. At the end, it will be a Gaussian random function.
Can you prove some almost true convergence or concentration?
No, this is more like a very soft proof. So we don't have any quantitative estimate right now, but it will be interesting to push it into almost sure or have some rate of convergence. Okay. So the key point is I use this 1 over z map, right? This reverse map. It maps outlier inside the disk. So if I know the convergence on the compact set, I know no outlier inside the disk. That means no outlier outside the disk from this 1 over z map. Okay. So how do I get convergence of this random characteristic polynomial? There's a general rule to prove convergence of random analytic function. If I have a sequence of random analytic function, if I know the sequence is tight and the coefficient of my analytic function converge jointly for every finite collection, then you can guarantee that this convergence will hold under this uniform local compact topology. So what is the tightness here? It means for every epsilon, there will be a compact set of random analytic function. So you can define a metric on this collection of random analytic function that gives you a compact set. If there's a compact set such that with high probability, with probability 1 minus epsilon, my family of function sit inside that compact set, then that's the definition of tightness. Okay. So how do we prove two things? One is the tightness, one is the finite dimensional convergence. We can do something to expand the characteristic polynomial. So first of all, there's one way to expand the determinant of a characteristic polynomial by writing it as z to the power k with this delta kn coefficient. This coefficient is called the circular coefficient. this coefficient is a polynomial function of trace A up to trace A to the power k. This polynomial is explicit. I didn't wrote it down, but it did it explicit. Okay. So if I know the trace, the distribution of a collection of trace converge to some random variable, that gives me the convergence of my random coefficient delta k. Because the polynomial is a continuous function, so by continuous mapping, you can get it. Then the question becomes the tightness. So I just need to check two parts, then I'm done. Okay. So how do we get convergence of trace? Convergence of trace in random graph terminology is to count the path. So our result says if I know D is fixed and let lambda L to be some Poisson random variable, we can show that for any finite decay collection of the trace, it converges jointly to some Poisson random variable. Okay. And you see this Poisson random variable is the coefficient of 1. Right, and sum over all the L that's divided by K, and you take L times the Poisson random variable lambda L. Okay, so how do we get this? First of all, you can think about A as a adjacency matrix of oriented graph with possible multi-edges and self-loop. I allowed my matrix A has value 0, 1, 2, even more than that. But we know C to CL will be the number of cycles that L in G. In random graph, in most of the case for random graph, this cycle counts will convert to a Poisson random variable if the graph is not too dense. Okay. So then you can do some approximation to show that trace of AK, which is the number of closed walk of MK, can be approximated by counting all possible ways to walk along cycles. So let's imagine I'm going to take a walk of length k from a vertex and come back to itself. So the easiest way is you pick a cycle of length L that's divided by k. So then you just repeat the loop k over L times, but I need to choose a starting point. So all possible way is L times CK. This is L times CL. That's the leading term of the trace. So that's also variable. At the end, the finite dimensional convergence of this trace reduce the understanding of short cycles in this random graph, and we know how to handle that. Even though this is not written in literature, but we try the moment method and just do some combinatorial counting that will give you the answer.
So what's the intuition for the correlation of the cycle terms for when they're relatively prime, the lengths? Because if lambda L's are independent, right?
Lambda L's are independent. Yes. Yes.
Some intuition on why
Because we're counting short cycles, so it's a fixed length. You should think about short cycles in the random graph are essentially disjoint. That's that. The long cycle might be wrong. A short cycle is okay.
I understand for one single trace that you're counting closed walks, but if you're taking several traces, like to look at the joint distribution, what are you counting? Because you're having row of traces.
So trace means I need to come back, right?
Just for one matrix here, you're looking at the joint distribution.
Oh, I'm just looking at A as the sum of permutations. So I think about it as a one graph, a graph, but you might have multiple edges along in some pairs. But that's negligible if D is fixed. So in the end, the approximation is good enough for us. Then we need to kind of tighten it. And the tightening, again, we need to do some expansion for the determinant. So another expansion. So previously, I expand the determinant and with the secular coefficient as a polynomial of trace. And there's another way to expand this polynomial by doing cofactor expansion. So we can write this secular coefficient as the sum of determinant, where this determinant of AI is by taking any principal block of this. Okay. So there's a theorem from Shirai that if I know the random analytic function, this random coefficient has bounded second moment with the correct growth rate. And you can show that this sequence is tight on the disk of radius square root r. This is not hard to show. It's just like a Chebyshev inequality. And in the end, we just need to calculate the expectation of squares of the secular coefficient, right? And the square of the secular coefficient becomes you take delta k and you expand along two blocks of the matrix, and you take the determinant of AI and AJ together. Okay, and if I can control the growth rate properly, that gives me tightness. And in this case, this is an easy task for Garcia Zadala, because if you have IID entries, you can easily show that if IJ are disjoint, the expectation is 0. So you have to make them overlap entirely. And the second moment of this determinant is explicit. So it's very easy to control. But for us, we need to think about how to expand this term in a better way. And here we use this exchangeability because we have very nice model. This is a sum of random permutations. So if I just look at any permutation, if I just permute either the row or columns, the distribution doesn't change. That helps us to reduce this second moment calculation to only 2 terms. The first term is the similar one as the ID case. I just overlap the 2 sets entirely. And the second term is the overlap is k minus 1. So they only differ by 1 element. The lower order term is exactly 0 because there's if you expand the determinant, there's some inversion number of the permutation. So if IJ is overlap more than 2, I can do a swap that cancel all the things. So there's by exchangeability, I can cancel everything if I have more than 2 overlaps. Okay. So in the end, we do a lot of technical combinatorial estimates. But since we have some independence between the different matrices, you can still handle it. And the second moment can be bounded properly. So that handles tightness. This gives you the proof for XD. Okay, now let's go to infinity. If it equals to infinity, this limiting function becomes much nicer. This Poisson random variable disappears, and you just get Gaussian random coefficient. And in the end, this normalized quadratic polynomial will convert to z square root 1 minus z squared. This is the deterministic part, and exponential of this Gaussian analytic function. Okay, this is the same limiting function in the paper by Bordenov, Shafai, and Garcia Zadala, where they have A being non-Hermitian I the entry of everything. So you can think about when I take D goes to infinity, this model enters the universality of I non-Hermitian. Again, tightness is already handled because we can handle tightness up to D equals big O root, little O root n. If I only care about D is n to the power little O1, I can handle tightness directly. Then I need to do my cycle count. Before, when I take these fixed, my cycle count are Poisson random variables. If I take D equals infinity, you can do Poisson Gaussian approximation of Poisson. So if I centered and normalize, I get Gaussian random variable again. That's the idea. At the end, you get Gaussian random analytic function. And if I just divide it by the trivial eigenvalue, I can show that this normalized quadratic polynomial converges to an analytic function inside the disk with no root. So that means second eigenvalue is bounded. So it's the same unified approach.
So here when these linear events, you know that it's false.
I believe this is true, but there's an issue with the cycle count. I just told you that short cycles are separate for sparse graph. Yeah. So you might need some other argument, but I believe the limiting function is the same. Okay. So the limiting function will be a Gaussian analytic function, and it has a nice structure. So if I just look at any 2 point on the disk and just calculate covariance, it is a log function. So it's a log correlated Gaussian field inside the disk. What happens for this YD? If I take the covariance kernel, it has the similar structure, but there's a order 1 correction. But if I send d goes to infinity, this Poisson field will converge to the Gaussian log correlated field. Okay, that's so everything is consistent at HT or point D. Okay. And I want to mention, inspired by Brian Hall's talk, I want to mention some thing we did for modal deformation. So we just mentioned that you need to take uniform random permutations, and we use the exchangeability and independence. But what if you perturb the uniform measure a little bit? You can look at evens distribution on symmetry group. Evens distribution satisfy this. If I take a random permutation, the probability is proportional to the theta to the power of the cycles in the permutation. So if I take theta equals 1, I don't care about the cycles. That's the uniform measure on the symmetry group. If I take theta greater than 1, it's a measure that's biased towards more cycles. If it is less than 1, it's biased toward permutation with fewer cycles. Okay. What happens? Very interesting that then the limiting measure is not a circle, it's some weird shape, and we don't know how to prove it. Maybe the audience have more knowledge and we can talk about that. So we're curious about what's the limiting measure. Okay. First of all, we don't know the analytic function for that. And is this some kind of deformation of Laurenti-Castel McKinnon? We don't know. And we don't know the support.
So for just one matrix, do you know the limiting law?
One matrix, you're still on the oh, and I think people already know. Yeah, it's been studied. Yes. Because you just understand cycle count, that's enough. And for evens model, you know the cycle count precisely. Another thing, this might be too hard because for fixed D, this is a sparse model. I'm still looking at the permutation with a lot of zeros. But we know Denbo and Basak has hard unitary or hard orthogonal matrix. They can prove the convergence to the Laurenti-Castel-McKay law. So it will be interesting to see if there's any modal deformation for hard measure on the compact group. So is there a way I can deform a little bit to get this kind of law? Maybe it's already known, but I'm not familiar with the literature, so I would like to ask this question to the audience. Okay. And let me conclude my talk. So we use a new strategy in the paper by Bordenov, Chafai, and Garcia Delada. We generalize it to study outliers of non-permutation matrices with dependent entries. The upper bound is a quick corollary from convergence of Cartesian polynomial. And it reduced to prove two things, tightness and finite dimensional convergence. Okay. The Poisson limiting analytic function itself is interesting. For d equals 1, it's been studied by Cook and Zattuni, and you can also look at the maximum module of this analytic function inside the disk. Another interesting from the random graph community is there's no way to get anything for the lower bound. It's really interesting. So we proved the upper bound, but if you don't know the convergence of Laurenti-Castel-McKay law, we don't know the second eigenvalue is lower bounded by square root d minus f1. And that's a very hard question for on the directed graph because you don't have the variation formula. So that's hard to handle. And another thing is we couldn't say anything for the uniform model because the sum of random permutation model for large D is quite different from the uniform model because, for example, when power of D, you will see multiple X in the sum if D is large, but uniform model is conditioning to be a simple model. So it will be interesting to directly work on this uniform model and get anything for the spectral gap. That's the end of my talk. Thank you for your attention.
For your simulation, you said that support the condition of these. Yeah.
There's a funny thing. There's a corner, so it's not convex if theta is very small. And for theta is bigger than 1. It's a weird shape, so it's interesting to look at it.
And do you know some value of theta where it's more like a
Theta, what?
something where this looks like a circle?
If theta equals 1, definitely you get circular shape. But I think for theta not equal to 1, you only get a symmetry along the y-axis, but you don't have the spherical symmetry.
I know it's going to be hard to say anything rigorous, but do you suspect that this deformation actually moves enough eigenvalues to affect the limiting measure, or could it be little o of 1 eigenvalues just moving towards the outlier, or little o of n? Sorry.
Or even for fixed D of a sum of random permutations, it's not a uniform measure.
Oh, right. Density has a
Spectral shape, and actually, I don't know. Like Brian Hall talked about this deformation from circular law to semicircular law. I'm not sure if there's a direct way to do the deformation from this distribution to this one. Because it's not exactly the twice of the real part. And this is 2 root D minus 1. This is 1 root D. Not exactly twice of the real part. But at the end, if equals infinity, it works.
Just this conjecture on the board is the issue the least singular values. That's kind of what's
So in this regime, only can handle this singular value. If you have random hard orthogonal hard unitary, you can handle this singular value, but this is way too sparse. Harder way to get around the value, but otherwise it's hard.
That's something you go, okay?